Hey everyone, I want to use this video to talk to you about discrete probability distributions. But before we do that, we're going to talk about what it means to be a discrete random variable and learn a couple things about them. So let me get started here. So here's the notes. So this is the top of the discrete random variables notes. So the first thing we want to start off with is the terms that we use a lot, and there's a couple that we're going to use a fair bit here. Let me start off with what a random variable is. It's just anything that counts or measures an outcome of an experiment of some kind. That's all a random variable is. It's just sort of the statistician's name for variable, I guess. I'm not entirely certain how they differ from variables, but there's some sort of technical difference that we're not going to worry about. Random variables can be either discrete or continuous. So a discrete random variable is one that takes on certain values, and a continuous random variable is one that can be anything in a range. So discrete random variables typically count things, and therefore are almost always integers. They don't necessarily have to be, right? You could count something to the nearest half or whatever, like if you were, I don't know, measuring by the half cup, how much water is in this bathtub, and you're measuring by the half cup, you could get halves or whatever. But that's such a weird example that it's just not a thing we're going to concern ourselves about. Usually they're integers, not always, but usually. Continuous, we're not going to deal with continuous in this video. That's going to be in the couple videos from now. It's the next chapter in the book. But it's anything in a range. So for instance, back to my water in a bathtub example, you could have any amount between 0 and however much water your bathtub will hold, right? So it could be literally anything in there, including fractions, as opposed to discrete, which are just usually whole numbers, usually counting things. In general, a quick way to tell the difference is how much versus how many, right? I would say how much water is in the bathtub, or how many people are in the room, how many soda cans does this factory produce in an hour, etc. Right? So how much is continuous, how many is discrete. It's not a hard and fast rule. You can play with the language enough to make it not work, but it works fairly well if you think of it that way. All right, so let's go through this. So here's what we're going to do. We're going to let our random variable be the number of heads that we get in three flips, three coin flips, right? So we're flipping a coin 3 times. We've done this before. And here is our sample space. We have seen that one before. And what we're looking for is how many heads we get in 3 flips where x is going to count that, right? So x equals 3 in this outcome here, and x equals 2 in this outcome, and x also equals 2 in this outcome, right? So in fact, there's 3 outcomes with x equals 2. Each of these things has a probability of 1/8. So if we're making a probability distribution, which is this thing right here, this is what we get. So x can only have 4 values in this, right? If we're flipping a coin 3 times, we get 0, 1, 2, or 3 heads. And the probability of each one is listed right here. So the probability of getting 0 heads, just say we get all tails, is just 1 out of 8, which is 0.125. And the probability of getting 1 heads in 3 flips is 0.375, because there are 3 different outcomes here. This one, and this one, and this one, all of which have exactly 1 heads in them, right? And each one has a probability 1/8, so we get 3/8 probability. So this guy right here is a probability distribution. We've defined these before, but I think this might be the first time I've used one. Probability distribution is the sample space, which is this guy right here, right? All of the possible outcomes of x are 0, 1, 2, or 3, along with the probability of each outcome, which I've listed right there. So we use these a lot. These probability distributions are what statistics is based on, essentially. Like everything we do from here on for the rest of the semester is going to involve probability distributions in some way. I believe everything we do. Yeah, I think literally everything from now till the end of the semester involves probability distributions in some way. Probability distribution is just a table or a graph that shows you all your possible outcomes and the probability of each outcome. Like I said, it comes in the form of a graph. We'll see those when we get to continuous distributions. You can also make them for discrete. We'll probably do a little bit of that too. However, this is for discrete or for small discrete distributions, this is probably the easiest way to display it. You just, what outcome and what's the probability of that outcome? And we're going to use these a lot. All right, so let's just quickly practice reading them. I'll pause for a second while I try to answer these. All right, let's go over these. So the probability that x equals 1. So the way you want to read this is this capital P means the capital P and then some parentheses means the probability of whatever's in the parentheses. So this is the probability of x equaling 1, right? So we can just look at there. It's 0.375, right? That's all that is. Oh, let me point something out really quickly. By the way, there's a point I want to make here about notation that you want to be really careful. It's very easy to use notation badly in statistics, and it can be very confusing. So here is what we do. Excuse me. Note the name of the capital. So we call the variable itself is called the capital letter. So if I want to refer to the random variable that counts the number of heads, I'm going to call that capital X. If I want a specific value of capital X, I will call that value little x. So that's why this right here is little x. This is a list. This right here is a list of values of little x. So that's why I've headed it little x instead of capital X. Similarly, is the probability of little x. So the probability that x equals 1 or that little x equals 1 or 0 is 0.125. Right? And that's what I've put here. The probability that little x equals 1 is 0.375. The probability that little x is greater than 1, and again, being really careful here, greater than 1 does not include 1. Greater than 1 is things that are bigger than 1 only. So that's 2 and 3, that's these. And you add those together and you get 0.5, 50%, which makes sense, right? If there's 4 outcomes, well, I'm not gonna worry about that. Probability that x is between 0 and 3. You can read this, by the way, as 0 less than x less than 3, but that's awkward and it doesn't trigger in your brain the idea that you want it to get across. The way I want to read this is the probability that x is between 0 and 3, not including 0 or 3. And I'm trying to give my brain the intuition necessary to easily identify which outcomes I'm interested in here, right? So after I do that, I'm going to say to myself, all right, what numbers does this include? Well, it's just 1 and 2, right? 1 is bigger than 0, and 1 and 2 are bigger than 0 and smaller than 3. So it's just these guys right here, which if you add those up, you get 75% or 0.75. And the probability that x does not equal 2, there's 2 ways to calculate this. We could add up, so x not equal to 2 includes 0, 1, and 3. So I could add up the probability of x equals 0, x equals 1, and x equals 3, or I could subtract from 1, which is what I'm actually going to do because that's easier. So if I do x not equal to 2, that's going to be everything except this. So I want to do 1 minus 0.375. So if I do 1 minus 0.375, if you recall, we want to do 990. So this is going to be 0.625 because 3 plus 6 is 9, 7 plus 2 is 9, and 5 plus 5 is 10. Or we want to do 9, 9, 10. So 0.625 is what you get when you subtract 1 minus 0.375. All right, now we're going to get into some little bit more interesting stuff. This is a question that we want to ask a lot. What is the mean of some probability distribution? In other words, in this case, what is the average number of heads that I should expect to get in 3 flips? Now, if you just think about it, it's not going to be hard to figure out what that average number should be, right? It should be 1.5. You get heads about half the time. We're doing 3 flips, so we should get 1.5 heads. Pretty straightforward. That is not a number you can actually get, right? You can't get 1.5 heads in 3 flips. You get 1, or you get 2, or you get 3, but you can't get 1.5. However, that's still what the expected value is, even though, which is kind of a confusing part of the name, right? Expected value sounds like the value you would expect to get, but it's not. It's the average value over the long run. So in other words, if we did this experiment millions of times, flipping 3 coins, writing down what x is over and over and over again, and averaged all those numbers together, the thing we would get would be the expected value, right? So that's what 1.5 is. So Expected value, despite the name, is not what the value that you expect to get in one trial. It's not even necessarily the most common value in one trial, although it often is. What it is the long-term average value if you repeated the experiment over and over again. It's the average value of the random variable. Now, I will say this. Expected value is just another word for average. That's all it is. So remember back at the very beginning of the course when I said we would learn mean and average, and those are two words for the same thing. Expected value is also a word for the same thing, except you really only use it in the context of random variables. So if someone is looking for the mean of a random variable or the average of a random variable or the expected value of a random variable, those are all the same thing. The way you find it with random variables, and I might as well do this, show you a little calculation on this, is this guy right here. So what your book does, which is one of the few books I've seen do this, I think it's smart. So many books will refer to expected value as capital E of X. I like this one better, mu of X. And the reason mu of X is better is because it's telling you the mean of X, right? That's what expected value is. It's actually the mean of X. So calling it mu of X makes perfect sense. Comports with the rest of our terminology and notation already. I like that your book does this. Most books call it E of X, but your book makes a good choice here, which is a nice change. Sometimes they make bad ones. So anyway, the way you calculate it is this. So the average value is the sum over all the values of the value times the probability. So if you're, let's say, a poker player, for instance, which, by the way, statistics was actually originally invented to help people gamble better. But within that, so poker players will often talk about the expected value of a hand. So they're thinking of it as payoff, so how much they're going to win, times the probability of winning that much. Similarly, if we're looking for the number of heads we're going to calculate the number of heads times the probability of getting that many heads. And then we'll add all those things up. So we can see the calculation over here, right? So if we have 0 heads, there's a 0.125 chance of getting that. 1 heads, there's a 0.375 chance of getting that, et cetera, et cetera. So 2, 3, and then you add all those up and you get the number we expected to get, 1.5, right? We said that we were thinking that on average, we were going to get 1.5 heads. I don't know if you heard that beep, by the way. That's me, not you. We're going to get on average 1.5 heads every time we flip 3 coins. And that's what we expected to get. So our intuition and the calculation agree with each other, which is a good sign. That means our intuition is making sense. Okay, so I want to pause for a second and let you do this. So calculate the random variable with this probability distribution. So here are the values and there are the probabilities of getting those values. I'll pause for a second and then I'll show you how to do it by hand. And then I'll do it on sheets and then I'll do it on a TI-84 and you can see all 3 and they're all not too hard. All right, so I'm pausing. Okay, that probably gave you enough time to pause the video and do this. So here's how we're gonna do this. So I'll do it by hand, very straightforward. I'll go ahead and annotate this, I guess. There's not much to this. What we're going to do here is -3 minus 3 times 0.2 plus -1 times 0.05 plus 0 times 0.05, 0.5. Oh, I'm going to need a much bigger screen for this, pardon me. Shoot. All right, I'm going to undo that. We'll just do it on 2 lines instead. Sorry, I don't want to mess up the thing I've got going here. What the heck? Oh my gosh. I need to go turn my Discord off, pardon me. Okay, let's try this again. I'll just go ahead and finish this up. 0 times 0.5 plus 4 times, I'm making decimals there, 4 times 0.1 plus 7 times 0.1 plus 0.1 plus 9 times 0.05. And so that's going to be equal to what we got, minus 0.6 minus 0.05 plus 0.4 plus 0.7 plus 0.45, and that's going to equal something. Let's figure this out. So we got minus 6.5, minus 2.5 plus 0.45, so I'm getting 0.9, 0.9. All right, hopefully I did that correctly. Oh, by the way, I know I ignored the 0 times 0.5. Obviously, that's 0. So I'm getting 0.9 here. Hopefully that comes out right. I think I've got this right. Yeah, hopefully I've got this right. Let's find out. So I'm going to go over and do this in Sheets, and then I'm going to show you how to do it in your calculator. So I'm going to solve this nonsense. All right, so let's switch over to Sheets, and we'll do this. So that was this one here. All right, so we had, pardon me, I'm going to have to put this in. So what I'm going to do here is, let's say this is outcome, probability. What? I didn't go back. All right, so -3, -1, 0.479, -3. Hello? Are we not here? -3. No. What? -3. All right. -1, 0.479. 0.1479. Wait, was it? No, there's no 1 there. Bad. Okay. And then the probability of each of these, this guy was 0.2, and then I forgot 0.05, and 0.5, 1, 1.5. Okay. 0.05, 0.5, 0.1, 0.1, and that guy. Let's make sure I've got that right. 0.2, 0.05, 0.5. Yeah. Okay, good. So that's what we've got for our data, for our probability distribution. So the way you can calculate the weighted average. So there's a command for it in Sheets called average.weighted, I think. Let's see. Oops, I forgot the equal sign, equals average.weighted, this guy right here. This is the one we want. And so that's what we're going to do. So it wants the list of values, comma, the list of weights. So my list of values go from A2 to A7. So A2 to A7, comma, the list of weights, which is B2 to B7, B2, comma, B7, oops, not comma, colon, B7, like that. And then it gives us, hey, I did it right by hand. Fantastic. Gives us the weighted average. So what it's doing there is that calculation that we just did, right? The one where it's just doing -3 times 0.2 plus -1 times 0.05 plus 0 times 0.5, et cetera. It's doing all that and giving us this. And it's called a weighted average, which I call it an expected value. It is, but the more common name for it is weighted average, where what we're doing here is we're averaging these numbers together. And this is sort of the importance of it. And in our case, we're using importance to mean frequency or probability. And that's the most common way to do it. But there are others. There are other ways to do these weighted averages, which I'll show you. You've actually used weighted averages before or had them used upon you. I don't know if you've used them necessarily, which we'll do in a little bit. But yeah, that's why the weighted average and expected value, same thing. No difference there. All right, so the other thing I want to show you is how to do this in a TI-84, if you would like to use that instead. That guy right there. All right, so here's my TI-84. I'm going to do the same thing I did before. I'm going to put in my data. So now, if you recall, the place you put in data in the TI-84 is stat and edit. That's the lists. So I'm going to hit the stat button and then go to edit, which is the first one. And then I'm going to put in my my values. So -3, -1, 0, 4, 7, and 9. And then in the second list, I'm going to put in the weights. So 0.2, 0.05, 0.5, 0.1, 0.1, and 0.05. And then I'm going to use one variable stats. Now, one variable stats. So I'll show you how to do it wrong first. This is going to be a really common mistake that people make. So I'll show you how to do it that way first, and then don't do that. So I'm going to go to stat and calc and one variable stats. And if you just put in L1, what it's going to do is it's going to average together the numbers -3, -1, 0, 4, 7, and 9 with equal weight. But they don't have equal weight, right? That some are more likely than others, and you have to account for that. So if I just hit calculate here, again, this is wrong. I'm getting an average of 2.66, which isn't correct. And the reason it's not correct is because it's not taking the probabilities into account. So let's clear this off and show you the right way to do it. So stat calc. Let's try that one more time. Stat calc, one variable stats. The frequency list is the thing that we want. So frequency list tells us that's our list of weights, right? So the list of probabilities of getting the outcomes. And I put those in L2, so I'm going to say L2 here. So second function of 2 is L2. Hang on, why did it not accept my second function count? It turned red, I thought. Second 2. Okay, worked this time, good. Then we calculate. And notice that now we get the thing that we expected to see, 0.9 for the average, which is the right one, right? Well, that's what Sheets got. That's what I got by hand. Great. Now, one thing to point out here, they give you standard deviation here, but only sigma, right? They don't give you S. And remember I told you that we mostly have S because we're mostly dealing with samples. Well, this isn't a sample. By giving a probability distribution, what you're saying to the calculator is, I know the likelihood of each of these occurring throughout the population. So the calculator knows when you use a frequency list that it is not getting a sample, that it's instead getting a population probability distribution. And so it only gives you sigma, which we'll talk about in a second what that means, but it means pretty much the same thing as it did in the other case where we found standard deviation when we just had a list of data. Okay, so that's how you do this on the calculator. So use calculator, use Sheets. I don't care which one you use. They do, Sheets obviously does more stuff, but is a little bit less convenient, I think, in this case, but not much less. So your choice. All right, I'm going to go ahead and switch back to the notes. Where are my notes? There we go. All right, so here is an actual raffle that occurs every year. This is the Santa Barbara Home Raffle. It's kind of famous around here. I don't know how many of you know about this, but this is a real thing. They raffle off a house, a very nice one, right? So this is actually from 2018 when I wrote this. So this is a couple years ago, and the grand prize was a house worth approximately $3 million. The tickets are $150 a piece. And they sell 50,000 of them every year. And then the proceeds benefit the Contemporary Arts Forum, which, if you don't know where that is, it is the art gallery by the library downtown on the corner of State and Anapamoo. If you ever want to go, they've got an art gallery there, and this is to benefit that, I believe. This, by the way, is a wildly simplified prize structure. The actual drawing has 2,500 different prizes, at least it did in 2018, all the way down to like $50 gift cards, which I don't know if I'd want a $50, like I would almost rather just lose than get a $50 gift card if my raffle ticket cost $150. But anyway, let's calculate the average outcome here. So in other words, the expected value for somebody who is buying a raffle ticket. So what we're going to do is, I'm just going to use these outcomes. We're going to ignore all the other ones, all the other potential outcomes that you could get, because that's a lot of typing. And we're just going to put in these guys. And the thing we have to do is keep in mind that the tickets all cost $150. So the actual amount that you win is this amount minus $150. Which doesn't, put a big dent in it for the grand prize, but does for 16th through 20th prizes, which are only worth $500 each, right? So you paid $150 and you got $500. So you're up $350, but you're not up $500. You're up $350 because you bought one ticket and you paid $150 for the ticket and got $500 worth of whatever for your $150. So X is going to be, so my random variable is going to be the amount that I am up after buying a ticket, which most tickets I'm not going to be up after buying because most of the time we lose, right? There's 50,000 tickets and I'm only listing 20 prizes here. So there's going to be 49,980 losing tickets. So I'm going to make a probability distribution and it's going to go like this. Each one of these things is the outcome, or is all the possible, or let me try this again. This row right here is all the possible outcomes. And there's a very easy outcome to forget. It's the most important one, which is you don't win anything, right? It's really easy to get yourself tricked into thinking, oh, these prizes are all the outcomes. No, there's one more. And it's the most common one by far, which is that you don't get anything, right? It's a donation to the Contemporary Arts Forum. You donated $150. So these are all the outcomes. You could win the grand prize, or you could win the first prize. I believe in 2018, I believe this was a car, and this was a trip, and I think this was a different trip, something like that. I don't remember exactly what it was. So you can get the house or the car or one of the two trips or whatever these things were. And then this is the probability of each of those happening. So for instance, if you have 50,000 tickets, the probability of winning the grand prize is 1 in 50,000, right? Because you had one ticket out of the 50,000. If you had, same thing here, same thing here. Now, this is 4th through 10th, were $5,000 each. So we actually have a 7 out of 50,000 probability of winning winning whatever the 4th through 10th prizes were, because there's more of them, right? So we have a 7 out of 50,000 chance of doing that, et cetera, et cetera. And so what we're going to do is we're going to take these things and we're going to jam them all into either the calculator or Sheets. I guess I'll just do it in Sheets. Yeah, I'll just do it in Sheets. And then we'll see what the average is. So I'm going to go ahead and take these and I'm going to go over to Sheets to my Untitled spreadsheet here. And we're going to say, so outcome probability, yeah, so this is fine. So outcome, we could have $2,999,850, right? So that's one of the outcomes. That's we win the grand prize. Or we could win the $50,000 second prize. So we had $49,850. Or we could win, I forgot what it was, 10,000, 10, 5, 1, and then 500. Okay. 98.50. Oop, that's too much. 50. Or we could win the 48.50. Or we could win the $1,000, which is $850. Or we win the $500, so it means we're up $350. And then there's one more big option, which is we could not win anything, so we're just down $150 in that case. Then I want to put the probabilities over here, and I'm going to put them in fraction form. I think it just takes fractions if I put them in. So I had a 1 out of 50,000 probability of winning this. To do that, accepting that, I don't know if it knows that's a number. I hope so. Or 1 out of 50,000 here. Or 1 out of 50,000, I think, out of this one. And this one was 7 out of 50,000. I forgot how much these were. 5 each? 5 each. This was 5 out of 50,000. I might have to make these formulas. 5 out of 50,000. And then the negative 150, so in other words, you lose $150. We only have 20 prizes here, so that leaves, out of the 50,000 tickets, that leaves 49,980 losing tickets out of the 50,000 that were sold. All right, let's see if it recognizes these as numbers. So we're going to get weighted average. Yeah, no, that's fine. Expected value. So this is going to be equals average dot weighted, this guy right here, of A10 through A16, A10 through A16, comma, B10 through B16. Nope, it does not understand that. Yeah, so it thinks that 1 out of 50,000 is text. So what we're going to go do is we're going to go stick equal signs in front of all these so that it knows it's a formula. So it did not understand it. So there we go. Same thing here. Yeah, sorry, I wasn't sure if it would interpret this as text or as a fraction, and it chooses text, which makes sense. So if you're putting in fractions, you have to do equals, or it won't do any calculations. Equals, and then equal. Oop, come on, click equals. Okay, there we go. So the expected value that we get is negative 87.95. I'm just going to call that negative $88. So what that means is when you buy a ticket that you can expect on average to lose $88 of the $150 that you are paying, right? That is a little bit misleading, right? Because that's not really what happens. What happens is you either get regular luck, just like almost everybody, and lose all your money, or you get super lucky and win something huge, or occasionally something not that huge. So the expected value of negative $88 is the average value that the Contemporary Arts Forum takes in per ticket sold, right? So another way to think of this is, let's say that you and 50,000, or you and 49,999 friends got together and bought all the tickets, right? One ticket a piece. You bought all of the tickets, and then sold everything that you won and split up all the winnings. You would end up down $87.95 per ticket that you bought. Similarly, if you and two friends or whatever got together and bought all the tickets, you would end up losing $87.95 per ticket. Another way to think of this, and this is the way I actually think of it when I'm doing these, is that the total value that the Contemporary Arts Forum takes in is 50,000 times 150 tickets. So if I do equals 50,000 times 150, what I get here is 7.5 million, right? So that's 7,500,000. Well, they only pay out a little over $3 million in prizes, right? So the total amount of money that they take in exceeds the total amount of money that they pay out. And if you just take that difference and divide by the number of tickets, the thing that you'll get is this, negative 87.95. Right? So another way to think about that is it's the total profit, like this is the profit per ticket for the Contemporary Arts Forum, which means that profit has to come out of your pocket if you bought a ticket, right? So you would expect, they're expecting to make money per ticket, you're expecting to lose money per ticket. Yeah. I mean, but that's part of the fun of the raffle, of course, and this is donation to charity. Because once in a while, right, you get the fun of winning $3 million, or every year somebody gets the fun of winning $3 million worth of house, or $50,000 worth of, I think this was a Mercedes in 2018, etc. Right, so it's you're buying the fun and the right to donate to the Contemporary Arts Forum. So that's what this represents. This represents how much money the raffle ticket buyer loses per ticket, and how much money the raffle ticket sellers win per ticket. That's what the expected value is here. All right, so let's go back to the notes. You can see all my tabs up there, can't you? Yeah. All right, so this is the weighted average, which is expected value, obviously. And I mentioned weighted averages, which are expected values. Weighted average is just another name for the expected values. And here's what I was talking about when I said you've had expected value, or you've had that calculation used upon you in the past. Grades are generally calculated by this method, and it's the same. That's the way I calculate grades too. That's why when I tell you the class is weighted 25% homework, 45% tests, or 15% per test, and then 30% on the final, this is what I mean. Those are the weights. That's how important I am considering them. What that means is that they have different importances point-wise. So for instance, 1 point on homework isn't worth exactly the same as 1 point on tests. And that's not worth exactly the same as 1 point on the final. In general, by the way, I'll let you do the calculation, but in general, homework and tests are worth almost the same amount per point. Not exactly, but very close. And then the final is worth more by about a factor of like 75% or something like that. So 1 point on the final is worth more towards your grade than 1 point on homework is, by maybe 75%, maybe double. I don't remember exactly, but it's quite a bit more. All right, so here we've got this person's English class. They've got 2 graded assignments, or they've got 2 book reports worth 5% each, midterm worth 20%, research worth 30%, research paper worth 30%, and a final exam worth 40%. And here are her grades: 90%, 98%, 84%, 76%, and 70%. And we want to calculate her grade. So before you do that, and I'll go ahead and pause the video and let you, or I'm not going to pause the video. You're going to pause the video. I'm just going to pause talking to calculate this grade. But before you do that, see if you can guess based on this, just the numbers here and the weights up there, what grade you think she's got. So I'll pause while you think about that and calculate it. Then I'm going to go ahead and do it on the TI-84, because I already did the other one on Sheets. So pausing. Okay, let's do this on the TI-84. So I'm going to share up the 84, and we're going to put in those numbers. So I'm going to go to stat. Let me show you how you erase things. There are 2 good ways. There are 2 good ways and 1 bad one to erase things in here. So 2 bad ones, I guess. So here's my cursor. I can hit the delete key, and that will delete 1 thing, which is, here, fine, there's only 6, but when you have like 30 things in there, hitting delete 30 times isn't great. A better way to do that is to go up into the header. I hit the up key, up into the header up here, and then hit clear, and then enter. And that will delete everything in a column, that's really nice. And then I'll show you the other right way to do that, other right way to clear things out of here, which is from the memory function. This is actually the one that I use the most. This one works great if you have a lot of stuff in there, like if you have, all 6 lists full, and there's tons of data in each one. That actually comes up some of the time in here. If I go to memory, which is the second function of plus, there's clear all lists as an option. So if you just go to memory and then number 4, that'll clear all your lists at once. If you have lots of data, that's the quickest way to do it. So let me go back here. Notice that it's all gone. Now I'm going to, okay. So here is some data that I've put in. Let me show you the wrong way to delete things. And you're going to do this at least once. Everybody does. So I'll show you how to fix it in a second. So if I go up into the header, and instead of hitting clear, I hit delete, right? That's a thing that you might think to yourself, oh, delete, that'll delete the data. Well, if I hit delete, it deletes the column, like it removes it, which is not what you ideally want, right? It's nice to have all 6 of your columns available. So the reason you might want to do this is that you can make a custom column, like, yeah, it was right there. Do you see how it says name here, and we're in this unnamed column? You can make a named column if you want to. This has on the TI-84 essentially no use as far as I'm concerned. You would never bother to do this. If you have a TI Inspire, it does have a use because you have to call all of your columns by names instead of L1 or whatever. And so naming it something convenient is actually a little bit helpful. TI-84, basically useless. So the way you fix this and get your L1 back is, and by the way, don't name that last column L1. If you do, it does not associate that name with this button. So trying to hit L1 to get a column that you've called L1 won't work. So what you want to do is this. I'm going to go back to stat and then setup editor. If I just go to number 5, hit enter, it'll give me this, and I just hit enter again, and I go back to my lists. Everything's back, right? And notice that it actually still remembered what was in L1, right? It didn't get rid of L1. It just kind of stopped showing it to you, which is a little silly in my opinion. Anyway, we're gonna go here and then hit clear to get rid of this. So yeah, if you hit delete on your column, it's setup editor. So stat, then setup editor, and hit enter again, and all your columns will be back to the default. That's essentially, I don't know why they call it setup editor, because it's more like list defaults. Like it restores all your default lists. Okay, so what I'm going to do is I'm going to put in Samantha's grades as well as the weights. And remember, so the things that you're averaging are going to go in L1, and then the importance of those things, the weights, are going to go in L2. So I'm going to put what she got on the assignments in L1, and then the percentages that they are worth in L2. Now you can do this as a decimal or as a percent, and it does not matter as long as you're consistent with it and then understand what the results mean. So I'm gonna put in the things that she got as whole numbers. So she got a 90 on the first book report and 98 on the second one, 84 on the midterm, something, 76 on the research paper, and 70 on the final. So 76 on the research paper and 70 on the final. And those were worth respectively 5%, 5%, 20, 30, 40, yeah, 20%, 30%, and 40%. And most people, when they see these things, 90, 98, 84, 76, 70, look at that and go, that's 2 A's, a B, and 2 C's. That averages out to a B. It doesn't, because they're not equally important. These 2 A's are both unimportant. So anyway, we're going to quit out of here. I'm going to go to stat, calc, one variable stats, frequency, my list and my frequency list are still correct from before. And so I'm going to hit calculate. And again, remember, by the way, if you reverse these, you could change which one was your list and which one is your frequency list. It gets a little confusing if you're not familiar with doing that, or if you're not comfortable with doing that yet. But if you are, then feel free. So list is the things that you're averaging, and then frequency list is the weights. So if I calculate, I get that, 77. Samantha has a C. She should have done better on the final and not worried so much about the book reports. So she's got a C, maybe a C plus, not in my class. No C pluses. Yeah, so she's got a C, 77%. Okay, going back to the notes. Standard deviation means the same thing in this context that it does in the context of just data. It is the average distance that one data value is away from the mean. But that average distance is a weighted average, right? And so it doesn't really change anything, to be honest. It kind of means the same thing. The larger the standard deviation, the more spread out your probability distribution is. It still means the same thing. And I believe that is the last thing that I want to say for this video. We're going to talk about some specific discrete random variables in the next video, but I think that's all I want to say for this one. So let me stop this share and say that, yeah, I'm just going to stop the video here, and I will see you guys in the next video.